Hi everyone, in this video we're going to discuss matrices and linear transformations. So what are linear transformations? To understand them, let's first try to decipher the word transformation. Transformation is nothing but a change from a transformation is nothing but a change from an input to an output. Okay, and so a transformation is actually just a function. For example, think of a function which is usually denoted by f of x, where f is the symbol for the function, x is the input, and maybe it evaluates to some value y. Okay, that's the output. For example, y can be 10x, where x is a value, a number on the real line. And for every value of x, I get an output from this function, which is 10 times that number. So for example, if x is 1, then I get a number which is 10. Okay, so that's an example of a function, and this is nothing but a transformation. So what are linear transformations? In linear transformations have a couple of special properties. These transformations are such that when you apply the function, so let's think of again not in the vector land or vector space, but in terms of this function that we just wrote. So whether this function is actually a linear function, because this function, if I apply it on a value x, x1, let's say there's some value x1 over here, and there's another value x2 over here. If I apply this function on x1 plus x2, then it is the same as applying the function on x1 and then adding it to the value of the function that has been applied to x2. So applying the function before addition or applying the functions after addition and then adding them together evaluate to the same thing. So that's the that's kind of characterizes linearity of a transformation. And there's also another property, which is that if I have this function would be linear if f of let's say some number 3 times x is the same as 3 times f of x. And you can see that both these properties are satisfied by this function 10x. And so 10x is a linear function on the real line. So similarly, we have linear functions in the space of vectors. And these transform vectors to vectors, right? Inputs are vectors, outputs are vectors, and they also have these two properties. Okay. Now let's understand linear transformation from the perspective of basis functions and basis vectors. And why is that? That's because think of a function. Just think of any generic vector. Let's say v. Let's say that was taking values v1 and v2 in 2 dimensions. This is an example in 2 dimensions. So we know that this function, so this vector, is nothing but v1 times 1, 0 plus v2 times 0, 1. And these two were the standard basis vectors, which was e1 and e2, right? Standard basis. So these standard basis vectors get, if I'm going to define a linear transformation or a linear transformation, then it's going to map all vectors to all vectors. So maybe all vectors in my input space to all vectors in an output space. For example, if you think of it in the 2D example, let's say there's a vector, in this case, let's say v1 and v2 are 2 and 3. Then there's a vector like this. It takes a value something like this. And this vector got transformed to another vector, which is like this, right? So maybe this is 10, 0, and this is 0, 2, maybe. So this vector somehow got transformed to that vector, right? Similarly, every other vector, so whatever is that transformation, every other vector, let's say that transformation is actually f. For simplicity, I'm going to use the same symbol for now. every other vector in this 2D space can also be given as input to this function, and it also maps to another. It also evaluates to another vector, right? So, but the nice thing about um, these linear functions is that we only have to look at the effect of the transformation on the basis vectors. Um, and that's the interesting property for linear transformations. Why is that? Because if we know how the function evaluates on the basis vectors, right, on the basis vectors, then we know that if the basis vector is scaled, then then we know how the scaled vector gets transformed as well, because this is a linear transformation. And we also know that any vector is a linear combination of these basis vectors, and we know that for a sum of two inputs, linear transformations are as good as evaluating the functions on the inputs themselves and then adding them together. So because of these two properties, thinking about basis functions, so basis vectors, how they get transformed is NF. So um, so let's say, and in fact, right here, actually, this um, okay, yeah. So so let's say vector 1 comma 0 got transformed to a vector a comma b, and a vector 0 comma 1, the second basis vector in this two-dimensional space, got transformed to c comma d. Then we can actually just write or represent this function f, or the linear transform f, as a matrix. Okay, matrix is just a representation, just a notation for how this function looks like. And in fact, the matrix is nothing but AB and CD. Okay, it's just the so let's say there was a, so just to repeat, let's say there was a linear transformation going from linear transformation that we want to look at. Then let's only understand how it acts on the basis vectors. It takes 0 comma 1, sends it to a comma b, takes 0 comma 1, sorry, 1 comma 0, sends it to a comma b, 0 comma 1 to c comma d. If we know how it acts on just the basis, the two basis vectors, then that function can be just represented using the values that function can be represented using the numbers that constitute the vectors that were output when that function acted on the basis vectors, right? So that function, when they acted on the first basis vector, gave me two numbers, a comma b, a and b. And when it acted on the second basis vector, it gave me numbers c and d. So these four numbers completely characterize that function. Just like in the previous example, this number 10 completely characterizes this function, because there is no, once I tell you 10, you know exactly what the function is. Take the input x multiplied by 10. Here, the function is characterized by this, I guess, a concatenation of two, these four numbers in this way, and this is called a matrix. It has two columns. It has two rows in this case. Why does it have two columns? Because there are two basis vectors in the input. It has two rows because the output of the function has vectors which are of the same dimension, which is two dimensions. If 1 comma 0 was mapped to a, b, and c, and 0 comma 1 was mapped to d and f, then the number of rows would be 3, because the output vectors are in 3 dimension. Okay, now, so what is the impact of this matrix? So let's say we know how this function transform the basis vector. So let's say for a generic vector v1 and v2, how does this function, what is the resultant vector that we get if we apply this linear transformation on a generic vector v1 and v2, which is represented by v1 and v2, right? So this turns out to be the way we will write it is to write A, C, B, and D, and then v1 and v2 right next to each other, and the way we're going to read it is as follows, right? So this is we'll read it as A times v1 plus C times v2 and B times v1 plus D times v2. Okay. Or in other words, this looks like v1 times AB and v2 times CD, right? So this is the resultant vector. This is the resultant vector whose first coordinate is going to be AV1 plus CV2, and the second coordinate is going to be BV1 plus DV2. Okay, I just wrote it. I took the B common, but just saying that the original, when 0, 1 was transformed to AB, I just multiply it with V1, and the original transform vector CD, I multiply it with V2, and then I add these two together. Okay, so this is precisely the same interpretation that we had when we talked about linearity. It's like saying we first act on the basis vectors, get these two resultant vectors, and then scale them with v1 and v2. And that's what v1 and v2, the vector v1, v2 was, right? So if you look at v and v2, it was just v1 times the first basis vector plus v2 times the second basis vector. So this was on the input side. And here you can see on the output side. So this is nothing but, maybe I should put F here, saying that, sorry, not F here. Okay. Yeah. So this is nothing but v1 times F of 1, 0 plus v2 times F of 0, 1, those two vectors, right? So anyway, so this is just a laborious way to say that a linear transformation can be represented using a matrix notation, which is just a container which captures the numbers needed to tell you what the transformation is. So once you know these, for example, these 4 numbers in this 2-dimensional example, then you can transform any vector in the 2D space to the appropriate vector, which is the output of this function. Okay. So as I just mentioned here, if the input vectors, if the basis vectors 1, 0 and 0, 1 were mapped to or resulted in a 3-dimensional vector, then the corresponding linear transformation would be A, B, C, D, E, F, right? Stacked next to each other. This is not a, so this has 3 rows and 2 columns. So you can imagine a similar thing happening where you can have 3-dimensional inputs, for example, 10, 5, and 4, getting mapped to 3, 3, for example, right? So you can also have output vectors which are smaller in dimension than the input vectors, right? So if we are going from lower dimensions to higher dimensions, so maybe from 2 dimensions to 3 dimensions, we are essentially introducing redundancy. If we are going from 3 dimensions to 2 dimensions, maybe we are losing some information, for example. We'll make this precise if needed later. So let me just tie this back to what is how is it relevant to machine learning. So first of all, there is this many of you might have heard of linear regression. Linear regression, there's a variation which is when linear regression leads to where uh, where you can predict not just a one-dimensional target, but multi-dimensional target. For example, you can have a output which maybe you can predict income as well as maybe health. Maybe health. Maybe health can be represented as a numerical score. Then maybe you can predict income and health from the demographic data, right? So linear regression, what it does is tries to find a matrix. Let's say it's matrix. I'm going to just represent it as W, and maybe once we train using training data, we learn this matrix W such that when it acts on the input demographic, maybe for a particular person, then we can make a prediction on both income and health. Sorry. So this would be an output vector, this is the input vector, and this is a linear transformation. That's why there's a linear in linear regression. Some of you might have seen neural networks. Neural networks are somehow are also functions actually, which map from, for example, images to labels, like cat versus dog versus fox, for example. And images can be represented as vectors. Even these labels can be represented as vectors. And it turns out that in neural networks, let's say the input vector is again x. The input vector is multiplied by a linear transformation, and it's again multiplied by some nonlinear transformation. Let's call it g. And then it's again multiplied by a linear transformation. Let's call it maybe w2. And again, it's multiplied by nonlinear transformation g, maybe g1, g2, and so on. So and then you get the final output, which is this output vector. Okay, so there is still linear transformations going on in neural networks. Okay, so this is it for this video. Thank you for watching.